So in this video we are going to evaluate this limit using the interest useful result. So using this result we are going to evaluate this limit. So yeah, this limit here. So let's see how to do that. Yeah, first of all, look at this function here. If you want to define this function, you know that denominator no, should not be equal to 0. So we know that denominator function is equal to 0 whenever x is equal to 0 and x is equal to n pi. You know that sine curve, right? Sine, here we have sine of x. So sine of x is equal to 0 at n multiple of pi. Right? So here 0, this is pi, this is 2 pi. Yep, sine curve is hitting x-axis, this axis at multiple of pi. So we had to remove these all files if you want to define this function, this rational function. So here we consider so x is not equal to n pi. N is an integer. Otherwise you cannot define this function. Why? The denominator becomes 0. So denominator, because we don't define those functions. If you want to define a function, make sure that your denominator is not equal to 0 for x values, right? So you have to exclude these x values from the domain of this function, right? Okay. Yeah, I just rearranged the function here. So this is your function. Same thing here. I put this one together, this bit together, and I wrote 1 over sine this way. Now I rearrange. I put an x below here. If I do something, you have to do you have to multiply by that factor. Then so you did nothing, right? You did nothing because this x goes with that x, right? So you can rearrange your function in this way, and you can consider these two x together. When you consider these two x's together, you can so you get x sine x squared over x squared, and here you have 1 over this thing here, sine x. So our idea is to use this useful result, right? Here look at this function. We can apply that result for this thing, and here I think we can apply this one, because so we know that x as x tends to 0, so it is clear that what is the graph? It is clear that x squared also goes to 0, right? So if you draw a small graph, so this is x squared and this is x. As x approaches 0, x squared also approaching 0. That's why we can write this. So now right, so let's take the limit here as x tends to 0. So you have the product of two functions. So we use the theorem, this theorem here. So limit of product of two functions is equal to product of their limits, right? So product of their limits. Let's take the limits separately. So limit of x tends to, yeah, as x tends to 0, yeah, this function, yeah, sine x squared over x squared and times limit x goes to 0, 1 over sine x over x. Yeah, so we know that as, yeah, x tends to 0, x squared tends to 0. We can, yeah, write x squared tends to 0 instead of writing this, yeah, sine x squared over x squared. Alright, so here we have, yeah, 1 over limit x goes to 0 sine of x over x, right? So look at this. I think we can apply this result to evaluate that. Yeah, so something here we have x both x here, right? And that quantity tends to 0, right? As that quantity tends to 0, this function approaches 1. Yeah, similarly, so look at this one here, this guy x squared, sine x squared divided by x squared. What is the limit of this? As that this quantity x squared tends to 0, yeah, this one is equal to 1. Yeah, this one is equal to 1. And what is the limit of this one? Yeah, so which is this result? Same thing here, sine x over x. So limit of this function as x tends to 0 is equal to 1. Yeah, so therefore the, yeah, therefore, yeah, so limit of this function as x tends to 1 is equal to 1.